Welcome to the first lab experiment of the class. The aim of this experiment is to observe the motion of some object that is moving at the same speed without changing direction. The object used in this experiment is a standard basketball. Applying Newton's second law, or equivalently the momentum principle, I will explain what is happening in this video. First, I use the tracker application to record the constant motion of the basketball. I then recorded two sets of observations using a spreadsheet, one which depicts ideal constant motion without the force of friction or any other force due to the air or the surface, and the other which depicts close to constant motion when the ball is under the influence of real life circumstances. In this video, the ball is being made to roll on a surface, and the origin of the coordinate system that we are using is at the center of the ball. The left side of the x-axis depicts the negative x-axis and the right side depicts the positive x-axis. The measurements were calibrated to the length of the ball, which is 0.24 meters, and the point masses were in the center as the ball was rolling. In the experimental model that is being depicted, forces such as the force of friction influence the motion of the ball. However, we simply use Newton's second law to calculate the final velocities at different points of times. To record the velocities at different points of times, I used the GlowScript program. So here is my computational model based on Newton's second law, which states that an object's acceleration depends on the net force acting on the object and the mass of the object. In this model, we neglect the force of friction and F net is 0 as the velocity of the ball is constant. The mass, initial position, and the initial velocity are all mentioned here, and the units for all these values are in SI unit. The time is set to 1.401 seconds, and the formula for Newton's second law is depicted over here. This is my entire code which is made on the GlowScript program. I will be using this code in order to perform all the calculations required in the experiment. I have already put in the values used in the experiment. The time step that I am using for my predicted model is 0.01 seconds, and I am using a while loop to find the value of the final velocity at different points of times in order to create an accurate graph. After assigning the required values to our GlowScript program, we can run the program to see the output. Here we can see that the position versus time graph is a straight line graph and position and time are directly proportional to one another. In the velocity versus time graph, we can see that the velocity does not change with time. This shows that the velocity is constant and there is no net force acting on the ball. In this graph, we can see the line chart representation of the experiment position versus time and the model position versus time graphs. And the reason why both these graphs are straight lines is because of the constant velocity of the ball and the presence of a net zero force. If the x-axis is flipped, this is how the graph would look like. These are the four forces that I believe are acting on a rolling ball in real life. The reason for variation in the graph of our experimental model is due to such forces. However, while performing calculations to depict constant velocity, we consider these forces to cancel each other out. After the initial push is applied, we wait for the ball to attain a constant velocity and then perform our calculations. The ball moves at a constant velocity due to Newton's first law, as no external force is being applied anymore. Hence, the net force acting on the ball will be 0. Note, we cannot explicitly state the total forces on the ball and how they cancel one another out, but I have made such assumptions as we are depicting the constant velocity of a moving object for which the net force should be 0. Conclusion. From this experiment using Newton's second law, we can show that if no net force is applied on an object moving in one direction at the same speed, the velocity of the object remains constant.